Alright, hello everybody. This is Lieutenant Timothy Mueller again, and this is going to be a little unorthodox video if you're used to what you've seen from me in the past. Right here I got an Excel spreadsheet, and we're going to go through everything that we've seen so far in Chapter 4, but it's going to be a completely fictional vessel that I just kind of made up. We're going to see some special, not so special things from listing, lolling, sine corrections, cosine corrections to kind of wrap up everything here in Chapter 4. So let's get started. So first things first is we got to talk about what is actually on this spreadsheet. So up here we can enter the original kg and the original displacement of our ship. Then we're going to assume that we have a weight addition, or it's a removal if you want to make a negative long tons. And you'll be able to get this when you come to DK school and see me. We're going to put the kg of the weight in this cell right here, and then we're going to say how off-center it is. So weight kg is always going to be positive. And then off-center location, positive is going to be to starboard and negative is going to be to port. Then for here, so say we have 100 long tons and we're going to put it at 12 feet for kg. Over here, it's going to calculate if we keep that current weight. So if we keep this 100 long tons, if we put the kg at 24.915, it's going to give us a negative GM. We'll be right at that critical stability. Then if we keep the kg, so 12 feet, it's going to tell us that in order for us to get to negative GM, or GM equals 0, we have to add, or we have to have this weight be 1,614 long tons. So a little bit more than 1 1/3 times the weight of this ship, just so you can understand what these cells are doing. Also, if we take weight added, I also have this little box here that assumes that we're adding firefighting water, and it tells us the capacity in cubic feet, capacity in gallons. Then it calculates how many minutes. If we assume that one 95 gallon per minute nozzle is working for 275.6 minutes straight, that's going to give us 3,500 cubic feet, or just over 26,000 gallons, which is going to equal 100 long tons. This here is for 2 gallon or 2 nozzles, and this here is for 3. Moving on down here, we got the new displacement. So it basically just takes our original displacement plus our weight added, adds them together. You'll see here, it goes there. Our new kg, so it just uses that formula that I showed you before and divides by the final displacement, gets that. It tells you how far our kg moved up. So we knew that we had 10 originally, then 10.154 here. So it's going to give us a difference there, and that's going to give us the shift to starboard. So if we said it was 10 feet off center, our center of gravity for the ship is going to be 0.769 over to starboard. Now, originally, let's say our original GM was 1.146. And this is just something that, based off of the writing arms that I just kind of made up for this vessel. Now, if we take this here, using the radian line trick, it calculates the new GM of the vessel. So here, it'll be just a hair under 1. Now down here, this is where I create all the calculations for sine corrections, cosine corrections, and the like. So it's going to give us a degree of inclination. Here I just put in random, not necessarily random, but just fictitious numbers for original GZ, so the original writing arm curve. Sine correction, so here would be our kGA for the sine correction, and then the cosine correction would be coming from our off-center location over here. So say for sine correction, we know that it equals 0 at 0 degrees inclination, so we would expect it right there. And then if we placed our weight 10 long tons off to the side, we see sine is in 19 and cosine is in 20. We would expect to see 0 for 0 degrees inclination, and then a maximum in row 20 at 0 degrees. So here we got that 0 for sine, and then here we got 0.769. This is less than that, 0.766. And then right over here, 0.766. So this is the maximum. So everything looks so good so far. Then the last thing that we get from this is the new GZ, so the new writing arm. So we go from an original here to this. I'm sorry, from here to here. Now all of this is graphed here. So this blue right here is the original GZ, the original writing arm that we had. The orange line is going to be our sine correction. So it's going to tell us how much we have to correct our graph based off of the vertical change in the center of gravity. And it works for positive and negative. So if the center of gravity goes up or down, it's going to calculate it correctly. Then for cosine correction, it does the exact same thing, but just for cosine. So to port or to starboard, it's going to calculate it correctly. In this orientation, everything to the right is starboard, everything to the left is port. Right here is 0, this axis right here, right where this curve crosses right there. And then positives, like we had done in the earlier lessons, our positives are going to be counterclockwise. Anything negative is going to be clockwise. So if we have a ship inclined over to port, then we see here we have negative righting moments. That means clockwise righting moments, and it's going to be pushing us. So instead of leaning over to port, it's going to want to push us over to starboard. All right, and then moving on from that, the first sheet was calcs, where you input your data. Original GZ just shows the original curve, sine and cosine corrections. Then new GZ is going to place the new GZ, so the blue line, in comparison to the original GZ, the orange line. So that orange line is never going to move. It's going to be the exact same as we saw here with this blue here. And then this blue line in this one, sorry for a little confusion on the colors there, but in this one, the new GZ is going to be blue. And that's going to have our cosine and sine corrected curve all superimposed, put into one curve. So now let's look at the different things that we can do with this sheet and see exactly how angles of list, angles of lull, and other things turn out. Now, a couple of the examples I'm going to show you in this video are going to be a little bit extreme, just so you can see how the graph's behavior changes when we add weight, high, low, really far off center, and something like that. So let's just start off here. We got an original kg of 10, original displacement of 1,200 long tons. We're going to add 100 long tons 15 feet high. So we add all that in. We should have no cosine correction because we have no off-center weight. And we see that right down here. New displacement's correct. So our new kg is going to be 10.38. Our GM, since we added weight high, we would expect to drop a little bit. And it does. We see new GM there, 0.76. And then original was 1.14. So let's take a look at how the curves compare with each other. We have the original curve of stability here. Our sine correction is this orange. It starts at a minimum, or it starts at 0, and then it rises to a maximum at 90, and then it starts dropping a little bit. Cosine, since we didn't have any cosine correction necessary, that cosine correction curve is just straight across. So the only correction we have to give in this chart is the sine. Now let's look at how it compares to original. All right, so the original, as we saw, was the orange, and then the blue here is the new. We know that we added weight high, so we expect that across the board we're going to lose righting arm, and we see that. The blue, which is the new GZ, is a little bit lower in every single spot than the orange. It's exactly the same at 0, because we know that sine of 0 is 0, and then there's small deviations as we go, and then the deviations increase as we go all the way to 90, which is right here. And then there's more deviations, but those deviations actually get smaller because of the sign of the behavior of the sine curve. Now, let's make this a little bit more detrimental to the ship. So we have a ship that weighs 1,200 long tons. Let's take 200 long tons, and let's add it 35 feet high. Now let's see what happens. So our new displacement is now 1,400 long tons, 1,200 plus 200. Our new GM is telling us we have a negative GM. Now, if you remember in the previous video, we talked about angles of lull and how the curve of stability, instead of staying positive all the way from 0 to 90 or past that, it'll actually dip into the negatives and then come up. Let's see if that actually happens. All right, so since we had no off-center weight, remember we had 0 still right here, but we had a huge change in that the kg of the weight that we added, it's actually going to jump up higher than that dip that I put in that curve. So we had talked about negative GM. We got that from the cells here that calculate it through the radian line. Now we see it graphically here because the sign correction is above the dip. Now let's see how the new graph looks. After a quick little calculation, we see here that it's mirrored along the origin. We start at 0, so it crosses at 0 again, so there's no writing arm at 0. So if that ship maintained a perfect inclination of 0, I'm talking within billions and billions and billions of an angle, it would stay there. However, any small perturbation, very minuscule, will cause upsetting writing arms. Then over here, if it's to starboard, we have upsetting writing arms, so negative, remember, is clockwise. And then here we see it crosses at 25. So this ship would have an angle of lull at 25. Then it has positive writing arms here, sending it counterclockwise. So it'll just kind of go right between 20 and 30, eventually settling out at 25. Now, knowing what you know about moments, we see that the writing arms between the two angles of lull here are very small. Very, very small compared to what we see with the angle of maximum writing arm here and here, and especially with what we see in the original. This means that the ship really doesn't have any energy to resist forces. So let's say on the starboard side, it doesn't have much energy that it can withstand forces trying to push it over to this angle. That's why lolling is so dangerous. There really is nothing that the ship is that's built into the ship to resist going from 25 degrees really quickly to negative 25 degrees. And that's a 50-degree jump. I think that can happen almost instantaneously. That's how people get hurt. So now we've seen how lolling happens. We see cross here, and cross here. We understand this here is stable because if we go clockwise if the ship tries to incline any to starboard, there's going to be positive moments going counterclockwise. And if it goes to port any further, there's going to be negative moments sending it clockwise. Same over here, but just in the other direction. Now, let's take a look at another change. So now we're back in the calculations sheet. Let's take the weight kg. So let's put that, the original kg was 10. Let's do something a little bit more realistic. It'll be at 16. Then for off-center location, let's send this all the way over to one side. So we'll say 16. So we're going to say this is 16 feet off center line towards starboard. Now we should have very serious cosine corrections as well as sine corrections. And we see that right here. We see values for all these. We have new GZs. Now let's see how the graph behaves. Going to the original, we have our cosine correction here in this gray. We have the sine correction in this orange. And of course, our original is in the blue. Now we see here, from the sine correction, our range of stability is going to be 0 to right around, if this here is 110, that'll be right around 103 maybe, something right around there. And then we got to do a cosine correction on top of that, so it's going to change even more. We see if there's no serious change, we're going to expect an angle of list right around, that's probably about 31 degrees, right in that area. Now let's see how the two curves stack on top of each other. And look at that. We have the original in the orange. Now we have the new GZ in the blue. The new GZ is calculated from the original. Then it applies the sine correction to get the correct vertical height of kg. Then it applies the cosine correction. Now we see here, right where that blue crosses the line, and crosses the horizontal axis, this line here being the horizontal axis, we see that's right about 31, 32. So our guess was pretty accurate. Now here, we have our stability pretty much coming all the way back to 110. That means we saw this, our sine correction actually came up all the way here, so we expected it to be right around like 105. But also look at what's happening with the cosine correction. The cosine correction, this axis here is 0. Yeah, this axis right here. So anything below that is negative. And we had talked about if you subtract negative numbers, it's actually a positive. So this value here from this axis down to the cosine is actually counteracting everything that's happening with the sine. which is going to give us that reserve buoyancy back when we're going for angles past 90. So that's actually a really cool observation you can make, but that's only on the starboard side. Look what happens over on the port side. So we have this angle of list here, and then all the way from starboard 31, 32 degrees, all the way to port about negative 102 degrees. We have negative righting arms, which means all of these are trying to push us counterclockwise, no matter where we are. I'm sorry, trying to push us clockwise. No matter where we are in this entire range, that's about 130 degrees, it's always going to try and push us negative, so that's clockwise. And only when it gets past 103 or so, only then is it going to give us these positive values, which is going to be counterclockwise. So that would be our range of stability all the way on the left side, because if we're inclined over the port 102 degrees, and then we impose a positive righting moment, which is counterclockwise, that's going to send us all the way around to 180. Now remember what I talked about with things that are special with ships that have a point of vanishing stability that's past 90 degrees, when we talked about the cosine corrections. Let's do an extreme example right here. So keeping our same ship, 1,200 long tons, 10 foot kg, we're going to have, let's say, 2,000 long tons. Like I said, this is a very extreme example. We're going to add the weight directly where the center of gravity is, so there's going to be no sine correction. And then for the off center, we're going to add that at 80 feet to starboard. So now we have these huge corrections that we have to make. Now, if we go here, the blue is the original curve, albeit very squashed down. Now this cosine correction is enormous, where the original righting arms were right around 6 or so. This cosine correction starts around 50. Now it jumps all the way down and is harming the ship's stability. How do these curves look? All right, so the orange was the original. Now the blue is our new GZ. Let's take a look at how it happens. So the ship here has negative, let's go from 0 to starboard. The ship here has negative righting moments. So negative means that it's going to give us clockwise. So if we have the ship at 0, it's going to go clockwise all the way to starboard, and it's actually going to sit right at 85, because that's where it's crossing that axis. Then anything further than 85, that is going to be positive, which is going to be counterclockwise. So the ship is actually going to be listing right around 85. Now we can try our best to destroy the ship by adding 2 million or so long tons. So now it's going even further up. But that ship is actually still going to maintain some sort of a, if we zoom in here, okay, so it's right on 90 there, but that ship is actually going to maintain a list right at 90. So it's not going to capsize all the way over to 180. And what a lot of people call turtling, which is where the ship is completely flipped over 180 degrees. That ship is actually going to stay right about 90 degrees. And it's pretty common. If you ever, just say, go on Google and do an image search for car carrier capsizing, most of them are going to be 90 degrees, 80 degrees, something like that. And that's because this cosine correction has a 0. Go back to here. It always has a 0 at 90. And then because it's negative past 90, since we subtract negative numbers from our original righting arm, we're adding to our original righting arm. Just a neat little observation. When you have an extreme example like this, you're not going to be able to capsize that boat. All right, so now that was an extreme off-center example with the height of that weight being added right at the center of gravity of the ship. So the sine correction is going to be 0. Let's go the opposite way. So now let's have a directly on center line weight addition, but it's going to be way up high. So we're going to add 200 long tons, 80 feet high. Now, how is that going to affect the ship? We saw that a cosine correction, no matter how extreme we made it, the ship is not going to completely capsize. Do you think the same would happen with a sine correction? Let's take a look at the origin or the curves as they stack up. Here's the original right here. We had no cosine correction, which is the gray, and then we have a sine correction, which actually is way above every single value that we have for these curves. So now there's going to be more of a writing arm due to having all this weight than there is that the ship can possibly have due to the shape of its hull. We would expect this ship to capsize. Does the actual curve of stability give us that information? Right here it does. Let's zoom in a little bit. So knowing what we know that negative values are clockwise. So if we tilt the ship any small degree to starboard, we're going to get a little bit of a negative writing arm, which is going to be a little bit of a negative writing moment, which is going to be clockwise. Then it's going to be a little bit more, and it never actually crosses this horizontal axis. So that means this ship is going to completely capsize. Now when you come to DK school, I'll allow you to have this sheet so that you can just take it back to your ship or whatever and play around with different weight additions, weight removals, anything that you can. If you are adventurous and you want to add your own little features to it, the password to unprotect it is going to be dcase, right down here, A31. However, if you don't know how to add these different formulas or do these calculations, I suggest you just don't try and unprotect it and just go with all the features that I have right here. Again, the tabs down here, calcs is where you can enter in your data. Original GZ is going to give you your original curve of stability that I just made up. You can go into calcs, unprotect it, and then make your own curve of stability. It's going to be right down here in original GZ. That's where you're going to input your data. Sine correction and cosine correction automatically calculates, and a new GZ just superimposes everything on top of it. Then the sine correction is going to be in orange, cosine correction is going to be in gray. And then if you go to the next tab, new GZ, it's going to give you your original curve in orange, and then your new in blue. When you get this spreadsheet, just kind of play around with all the different weight additions, add weight high, add weight low, add it to port, add to starboard, and see what happens. Do your own calculations on pen and paper and see if you get the same numbers that it gets here. So this does it for chapter 4. Thank you very much for listening. I hope you enjoyed this video and learned something from this chapter. The next chapter, we're going to talk about what's called loose water. So we're going to talk about free surface effect, free communication effect, and virtual rises in the center of gravity. It's not going to be actual changes in the center of gravity like we've calculated before. It's going to be virtual rises. We're going to see some neat formulas. We're going to derive those formulas, and we're going to use it to see if ships can survive certain conditions. But until then, I'm Lieutenant Timothy Mueller, and have a great day.